Okay, good morning, students. Only you? Only 5 of you? How about others? Where is Mariam, British, Kachan, Akbar, British? So today I want to finish my chapter 2. Okay, I want to finish my chapter 2. So we're going to start now for the classes. Please do Roger, your friend, came into the class. Okay, so today we're going to learn about arithmetics. Okay, so what is arithmetic? It is actually a branch of maths that study about numerical operations. Okay, so this numerical operation can be include your addition, subtraction, multiplications, division, and it also can be your roots, logs, and exponential. Okay, so before we go any further, I want you to understand about the terms, okay, where this term we will use it later, okay? So carry is the main term, okay, but the carry can be divided into two parts, which is carry in and carry out. Okay, when we talk about carry, it is actually a digit that transfer from one column to another column for more significant digit. Okay, so the first one is the carry in, where the value 1 or 0 would be added into the next column. Okay, for carry out is the value that moved to the next column. As you can see here, the carry out would be at the sum part, while the carry in would be in the front. Okay, in the front of the next column. Okay, so usually you're going to have your carry out first, only then you carry in into the next column. Okay, so you carry out from the existing column. Okay, then this carry out will be moved to the next column as a carry in. Okay, so far do you have any question for this one? So next, this is the binary and hexadecimal additions. Okay, so as you can see that 1 plus 1, you will get 0, where you will have a carry out here. But this carry out, you will bring into the front as your carry in. Okay, can you see this? So this would be your carry out, where 1 plus 1 is supposed to be 1, 0, right? So this one you will be bring down as a carry out, and then this one you will bring it to the next column as a carry in. So it still will be bringing the carry outs to the front column as your carry in, and then you will keep on do the addition until you finish all of the working steps. Okay, same goes with your hexadecimals. Okay, so like hexadecimals, you have rearranged them like this. Okay, you cannot do it by adding them directly. So you have to convert them to decimals. Okay, so how does this f plus a equivalent to 9? Who knows about this? Oh. How come it become 9? Because 15 plus 10, you will get 25, right? So 15 plus 10 equivalent to 25, where this one already more than 16. Since it is more than 16, you need to minus 25 with 16, then you will get 9. So this 9 would be the value here. And this 16 would be the carry out. You're going to have your carry out, and then you will carry the 1 into the front column as your carry in. So far, do you have any question for this part?
No, miss.
Confirm. I'm not going to repeat it, eh? Sorry. So this one I will run it out. When you're going to have your carry out here, like one, and this carry out will bring to the next line. Can you see this? Can you see? Line 2, 14 plus 4, you're going to get what 18, okay? And then you're going to add the carry in 1. That's why your value is 19 here. Okay, so 19, it is exceeded than the 16, so you will get 19 minus 16, so equivalent to 3, right? Correct or not?
Yes.
So you're going to have your carry in here, and you will do as we have carry out here. Okay, you have a carry out, then this carry out will be bring to the front column. Okay, so you can add it up. Okay, 8 plus 2 plus 1 is equivalent to 10. Okay, so 10, you need to convert them into hexadecimal value, which is D. Okay, so does this exceed? Does this exceed? No. Since it is not exceed, we doesn't have carry out, so we put it as a 0. And the carry in also would be 0. So 0 plus 4 equivalent to 4, so there would be no carry out. So this is how does the things looks like. Okay, so far do you have any questions? Okay. So far, do you have anything you want to ask about these things? No? So let's proceed. So about subtraction, it is the same definition as how you do your additions. Okay, you still need to do, when you do the borrowing, you need to borrow from the front. Okay, so 1 minus 1 is equivalent to 0. And this one, 0 minus 1, does it mean minusable? No, so that's why you borrow from the front. So this one will be 0. And this one you will get 1. So 1 minus 1 you will get 1. Understand? Guys, do you understand? Why does this, when we borrow this one, why we 1 minus 1 will still get 1? Why, guys? Ah. Okay, so I hope you understand this part. Same goes with this. Okay, you need to do the borrowing component so that you can see how does they borrow and people borrow. Okay, so as for your hexadecimal, you need to convert them first. Okay, so far, do you have any question? So, next. we have our numbers. Okay, so numbers can be divided into two. The first one is the signed number, the second one is unsigned number. So when we talk about signed number, it would be your positive and negative integers number. Okay, if we say unsigned, it only represent the positive integer numbers. Okay, so signed number need to be declared explicitly, while unsigned no need. And usually the signed number you reserve 16 bits. Okay, 16 bit is equivalent to 2 byte memory, where 8 bit equivalent to 1 byte. Okay, so the range value of unsigned of the signed number is negative 2 to the power of 15 until positive 2 to the power of 15. While unassigned, we start with 0 as your first value. Okay? So, before we going further for the chapter 2B and 2C, okay, you need to understand about the term of two complements, overflow, and then we're going to have first complement. Okay, so two complements. Two complement is the most common method to represent the signed integers on the computer. Okay, generally fixed point binary values. Okay, so how do we know that our numbers have a complement? How do we know that we have numbers of one complement, two complement? How do we know that? Anyone? Anyone know? Mahru? Hmm. So if we want to know, we need to check the leftmost bit where we check for the most significant bit. Okay, whether it have 0 or 1. Okay, do you have any questions as for now? Okay, so overflow is happen when your calculation the number is resulting an error due to the result no longer fitting in the stored format. Okay, usually it will involve the sign numbers. So as you can see here, 0 plus 0 would be 0, 0 plus 1 it would be 1. Okay, but this one, 1 plus 1, you're going to have a carry out 1, you have a carry in 1. Okay, so 1 plus 0 plus 1, you're going to get 1, 0 also. So you're going to have, you bring down your 0, you will have your carry out 1. And this one, when you go into the front, it will be your carry in, right? But this carry in does not fit inside all of these numbers. So this known as an overflow when you drop it down into the places of your sum. Okay, so this is known as overflow. Okay, so next, the sign numbers. First complement can be obtained by changing 0 to 1 and 1 to 0. Okay, so original binary numbers, okay, usually we will make it as a reverse value of your original binary numbers. As you can see, the examples here, when we say 101101, this is the original binary numbers. When we do the complement for each bit, where we need to change from 0 to 1 and 1 to 0. So this would be the first complement. Okay? For second complement, where you need it will form by taking the first complement of the numbers, okay, and then you add 1 to the less significant bit position. Okay, so just now you have your original value, you have your first complement, and you add another 1 in to form your second complement. So you will get this. Okay, so now I want you all to try this value and see. Find out the first complement and second complement. Now, later I will find a person to share the answer. Okay, let's try with Aaron. What would be the answer for the first complement? Aaron,
Is it okay if I screen share or just say the answer?
just share the answer.
Okay. Wait, ah.
Um, wow, good. Okay, thank you. So let's go for Miriam. What would be the second complement?
Actually, I don't know, miss. I couldn't understand.
You couldn't understand or you did not focus.
I think I missed some of your explanation because I just come in.
Oh.
Mm.
Okay, so let's see here. I give you an example. So for example, I have my binary numbers is 101. So this is my original. Okay, so the first complement is they said that you change from 0 to 1 and 1 to 0. So it means that this original 101, you change it into 010. So this would be your first complement. Okay, and then for second complement, they said you need to add 1 to the least significant bit. So add 1 to the LSB position, this one. Put a sign plus here. Okay, so 1 plus 0 plus 1, so you have what? 1 0, right? So you will bring your 0 here and you will have your carry out 1. So you have your carry out, you bring this carry out to the front as your carry in. Okay, so 1 plus 0 plus 1 still get 1 0. You bring your 0 down here, put your 1 as your carry out, and this carry out bring to the front as your carry in. So 1 plus 1 plus 0, you will still get 1 0. And you will bring the 0 down, and this one you will bring it as your carry out. And this carry out 1, you will bring it to the front as your carry in. So since this one does not fit with these 3 bits, so it will become an overflow here. So this one would be your overflow. That's why this would be your second complement. So far, do you have any questions? Mariam?
Yeah, good.
Good.
Yes.
Aisha,
Yes, ma'am.
do you have any questions?
No, ma'am.
No. Okay. Okay, so next, we're going to see how does the sign number being represented using your second complement, your positive number. Yes, just now all of us know that your numbers can be divided into 2, correct? So, which is the first is your positive numbers and the second one is your negative numbers. So, positive numbers, usually we have put a positive sign in front plus 4, negative 4. Okay? So, usually for if we want to identify the numbers is positive or not, usually they will add a significant they will add a 0 at the front of your most significant bit lah. So most significant bit usually would be here, your left hand side. Okay? So your left hand side would be your most significant bit. If we put it in the right hand side, it would be your less significant bit. So if they put here in the front 0, it means that your value is positive. So the true binary, it will be start from here. Okay? So far, do you have any questions? It same goes with your negative numbers. It's just that the sign bit would be 1, not a 0. Okay, so 0 means positive, negative equivalent to 1. Okay? So, as for now, okay, we have our positive values. For example, I give 13. Okay, still remember how do we convert the 13 into binary? Yes? Okay, so if yes, you just convert them as usual. It's just that you have add another column for your sign. So if the sign is positive, we should put plus. Okay, same goes with this one. If your sign is negative, we will put it as a 0. Okay, so can you see the differences between these two things? Do you have any questions that you want to ask? Do you have any
No.
questions? No. Easy? So let's have a 5 minutes break before we continue for the next part. Okay? 5 minute breaks, go to the toilets, grab your coffees and come back. Is everyone back? Okay, so let's resume. Before that, let us do some recap. How many types of number that you have learned before?
Sorry, miss.
How many?
What?
How many types of number that you have learned before? In last chapter 2E, how many types of number that you have learned? Hmm.
Sorry, miss. I don't. Sorry. Echo.
Huh? Again?
Do you explain? I don't understand the question. You
I
mean like
asked.
binary?
No, type of
No?
numbers. Just
Type.
now you only learn type of numbers. Itu numbering system, the one that you mentioned, binary, so on, is the numbering system type. This one is type of numbers. Type of numbers. You baru je belajar tadi. You just learn just now.
Positive? Negative?
Positive, negative considered as what type of numbers?
Positive is 0. Negative is 1.
Miss
No,
integers?
no. That is the names. What is the name?
Natural number.
No. Flashback. What was the type of numbers? You only learned now. Not even 5 minutes.
Arithmetic?
Okay, arithmetic. Good. So, under arithmetic, you have what types of numbers that involve? So you have two signed and unsigned numbers. Aiyo. This is the simple positional system. Still remember this simple positional system? Still remember how do we do it? Guys, we have 200 slides to be run today. If you did not communicate with me, I will just read my slides. I will not explain it. You choose one. You want me to explain or you want me to read the slide?
Explain.
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 I want your communication with me. Don't let me speak alone.
Okay, miss.
Okay? Next. Why do we need binary digits? Because each of your states use a single binary digit to represent them. Okay? Usually we only have two states and only two different states, which is on, off, true, false. Okay?
Miss,
Ah,
you not sharing screen.
I tak share screen. Okay. It's been so long. Only now you tell me I didn't share screen.
Sorry lah.
Okay. So, as you can see, this is only a recap, okay? So, let's go for 2B. Okay, we go for our numbering system. We start off with a simple and cheap where your switch can be on and off, and we collect lots of them together and define an order for them. Okay, so you can use that collection of switches to represent anything that you like. It can be your number, character string, pictures, machine, instructions, your music. Okay, so using the switch pattern for labeling, so you can label your object. Still remember your labeling yesterday? Okay, so
Yes.
we call a label that can be used to tell one object from another a representation of your object. So that's why yesterday when I asked you to do some research, find out what would be the differences between the labeling that being used, okay, for the product. For example, you provide me the examples such as cosmetic product, food, clothing, and what else. So all of them have their own significance labeling style. Okay, so we assign each category its own switch pattern and use that as its label. If we have 8 category of the object, therefore we need to have 8 different labels. Okay, if we have 8 different labels, we need to have 8 different switch patterns. Okay, so this is the examples of the switch pattern that we always use. Okay, so if there are 8 categories, we need 8 different labels, and we need to use an ordered collection of 3 switches. Okay, each can be on or off, so we will get 8 different patterns. Okay, so for examples, we have off, 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 on, off, on, off, off, on. If you can see that the pattern here is off, on for the first column. The second one is off, on. The last one will be the off, off. Okay, you can see the pattern based on the categories here. Okay, so based on this one, each of these represent an object for different category. Okay, so if we human, we can understand using the term of off and on, but does our machine understand? No, right? So that's why we need to use the bit string. Okay, so given that we want our representation to be independent of hardware, we abstract away from the details that you have on off, okay, and work with the bit string where it is an order collection of 0 and 1. Okay, so every representation of your object will be a bit string of finite length. So have a certain fixed range of your bit string will be used to represent your object. Okay, if there are 2 objects that is having identical representation. Okay, so we cannot tell them apart. Okay, so we obliged to say that they are the same thing. Okay, for example, they are represented by the identical bit string. Okay, so this one we will consider them to say they are the same. Okay, just now we have on off, right? So when we use the bit string to label the object, you can see like this. As I said, 0 considered as off, 1 considered as on, right? So when you convert them into a bit string, it will look like this. Did you see? This is the pattern that I said 0, 1, 0, 1, 0, 1, 0, 1. So we have 8. 0, 0, 1, 1, 0, 0, 1, 1. Okay? And the third column will be 0, 0, 0, 0, 1, 1, 1, 1. Can you see the patterns here?
Yeah.
Okay. So what would be the fourth column would be? What would be the fourth column? Value.
1000.
No, it would be 0, 0, 0, 0, 0, 0, 0, 0. As you see the pattern, the first column you only have single one, correct? The second column you have double 0. The third column you have false 0. So these things, it is doubled up by 2. So the next one shall be 8, 0. Do you understand that?
Yes, Miss.
Okay. So why only 0 and 1? Okay, so the power of bit string lies in the number of bits that we string them together. Imagine that we use 4-bit string to label an object. How would be the different category would we label? Okay, so just now I said 8 different bit string, you're going to have 8 different labels. What if we have all 4 bits? What would it be? So, as they said here, we can obtain the set of all 4-bit sequence by adding either 0 or 1 to the left-hand end for each of these 3-bit sequence. Okay, so when we add all of this extra bit, okay, we have doubled the number of the possibilities. Okay, so so each time when we increase the length of the bit, we double the numbers of the sequence for 0 and 1. Okay, for example, we have 1 bit. 1 bit, it means that we have only one value. If we have 2 bit, it means that we have 2 times 2, where we convert the representation 2 to the power of 2. Okay, when we have n bit, for example, I have 7 bit. So how would be the representation of 2? It will occur. Anyone? If 1 bit, you only have the occurrence of 2, 1. If you have 5 bit, you only have 5 occurrence of 2. How about 7 bit?
Two power 7.
2 power of 7 of the representation, what would be the occurrence? That would be the occurrence. Or the multiplication of the possibility. How many times?
7 times.
Yes, you have to times it for 7 times. So you imagine if you have 1000 bit, do you really need to use the multiplication for the possibility? I think it would not be that easy, right? So because you need to keep on repeating right up the occurrence for 1000 times. Therefore, they give you the simple representation to ease us as a human. Okay? Can you see my slide? Are you the same slide with me?
Okay.
Yeah. Okay, so there are lots of different bit strings. So for example, my laptop have 16 gig RAM. Okay, so 16 times 2 to the power of 32 memory cell, and each of them are ordered collection of 8 bit. Okay, how do we calculate this? Do you remember we need to extract the information first? So we have 16 times 2 to the power of 32 memory cell, right? And each of them have 8 bit. So how can we do this? So you need to make all of the value having the 2 as the base power. So 16 is 2 to the power of what?
4.
4. 2 to the power of 4. So this one would be plus or add. 2 to the power of 32. Huh. If we use 16 times 2 to the power of 32, right? We use times, but when we convert the 16 into 2 to the power of 4, so the operation here would be add or multiply?
Add.
Add. Why add? Why we need to add? We did not use the times. Huh. So go back to your log understanding, your base understanding. Okay? So how about the value of 8? It would be 2 to the power of 2 to the power of what?
3.
3. So 2, 4 plus 32 plus 3. Does we get 2 to the power of 39? Is it the same?
Yes.
Okay. So 2 to the power of 39, when we convert into a normal form, you will get this large value. Okay, so you're going to have this much value for switches that each of them can be on and off. So when you buy your computer, you shall know. When you have this kind of information, you can calculate already how many switches that involved in your machine, in your laptop. Okay, so at any time, the machine's memory hold 1 out of 2 to the power of this different bit sequence. Okay, that's many times numbers that we provide a different label for every atom in the universe. Okay, so usually it would be impossible to try out all of the string. Okay, even though we took out every computer that has ever been made, okay, and every computer ever will be made, okay, things that have exist and the one that has not exist yet, and we divide the task between them, it still does not possible to run through all of these big strings, okay, in the lifetime of your universe. Okay. So how many bits that actually do you need? In principle, we can devise the bit string that are long enough to represent anything that you like. Okay, but how many bits that are needed to guarantee that a different bit is available for each of item that we know or we might encounter. Okay. So due to this reason, there would be a way to work this out. Okay. So here comes the reason why we need to use the log base 2 and bit. Okay. So this one we have to go back to your math class. How many of you have not yet taken your discrete math class? Raise your hands. Maths for computing. So I hope all of you understand about the log, about the base, and how was from the log converted into the power. Okay. So for this slide, do you have any question about how does the log being converted into the power of something, base something something? Hello?
Yeah.
Got issue or not for this one? Because this one usually I did not explain because it's supposed to be the basic understanding. How was the log being converted into into the power? Where these two things is actually means for each other. They provide the same meaning. Hello? Hello?
Yes, miss.
Do you have any question for this slide? No.
No, miss.
No,
No,
miss.
miss.
Okay, so choosing the bit string length, if we know the length of a bit string, we can work out how many different bit string it offers. So usually an bit string can accommodate any 2 to the power of n bit equal. Okay, so for example, if we know how many different values that we need to distinguish, we can work out the amount of information that we need to capture using the value of log base 2 n bit, where this n is the size of your set. Okay. And usually it will represent each item using the bit string of length n. Okay, where this n is the integer, which is equal or greater to the log base 2 n. So the number of redundant bit string is 2 to the power of n minus big N. Okay? So a range of whole numbers. If you want to represent a range of whole numbers, we can work out how many different bit strings need. So we can do this because any range of the whole numbers give us a countable set. So the whole numbers is usually range from 0 to 9. It contains 10 numbers. Okay, so it requires 10 different bit inputs. Okay, so the whole set of the numbers in the range of 150 and 1200 contains 51. How do they calculate? From 150 to 200 is become 51 members. Anyone can explain this one? How come 150 to 200 it will have 51 members? But if we do the normal calculation, 200 minus 150, you only get 50. How come this one you have 51 members? Anyone can explain? Okay, if you cannot explain, then I let you to figure it out by yourself. I'm not going to waste my time since you don't want response. So we can use this information to tell us what the length of the bit string that will provide enough different bit sequence. For example, you have 10 numbers. So you need to use the value of the formulas that have been provided, log base 2 n. So you will convert them log base 2 10. Okay? So you're going to have 3.32 bits. So usually 3.32 bits, we need to do what? How come it become 4-bit string? How come it become 4-bit string? Anyone know? How do we get a 4-bit string? Huh? So our bit cannot be having the point value, right? So we round them up into 1 bit. That's why you're going to have 4-bit strings. Okay? So when we have 4-bit string, we need to use 2 to the power of n, which is we put 2 to the power of 4. So this bit string that you have find here would be represent your small n. So you will get 16 possibilities. Okay? So does how come you have a 6 redundant bit sequence? It is because your numbers you only required 10. So you have 16. So 16 minus 10, you will get 6. So this 6 would be your redundant bit sequence. Okay? So it means that 6 of the 4-bit combination would not be used because this is the extra capacity. This is the extra one. So usually this extra we does not use at all. Okay? So we only use 10 only. So what do you understand what is going on here?
Yes, so means it became 4 because there's no such thing as 3.32, so they rounded it off.
Yes, they round it off
Okay.
because if you see that our bit is only a solid whole number. So it is not logic if you split your whole number into point form, right? Even your data also, you did not split them into half. Correct. So the point form usually we round them up into 1. So that's why we have 4-bit strings. Understand?
Okay.
Okay, so now I give you, for example, we have 20 numbers. Tell me how many bits, how many bit strings, what would be the possibility, and is there any redundant bit sequence? Okay, so do it now. I want to see. It's only the easy way. It is easy question. Okay? So the question only requires you to find 20 numbers for each of the requirement, the bit information, the bit string, the possibility, and the redundant bit. So do it now. So the formula, do you know the formula? Log 2 n and 2 to the power of n. Are you guys done? Okay, Nishimura, can you tell me what would be the value?
The value would be log base 2 to 20.
Uh-huh.
So it will be 4.321. And if you round it up
Uh-huh.
to three significant figures, it will be 4.32.
Okay, proceed until all. How about the bit string?
The bit string, right?
Ah,
Is it like 4?
okay. Wait.
4-bit string?
So it will be looks like log base 220. Am I right? How
Yes,
what would be the value?
321.
4.321 bit. So what would be the bit string that you will get from here?
4.
No, I already mentioned it is not.
5.
Yes, 5. Why 5?
Round it up.
Yes, because our
Okay,
bit
sorry.
would not exist as 0.321. We rather round it up as 5 instead of we reduce the value. Okay? So how about the possibilities? What would be the value for the possibilities?
32.
32. How come it
32.
become 32?
Miss, because 2 to the power 5.
Yes, 2 to the power of 5, it's become 32. So is there any redundant bit sequence? Is there any? Huh. Do we have any redundant bit sequence?
12 redundant bit sequence.
How come it become 12 redundant bit string? How do you get this 12? Huh.
Because 32 minus 20.
Yes, 32 minus 20. This 20 is what we required to be used only. So this 12 would be the extra. Okay? So far, are you clear? Do you have any question for this part?
No.
Easy, huh?
Yep.
So this is the labeling only. So we choose the 4-bit item that we want to represent. Okay, so each number has their own different representation. Okay, So for this one, don't have any questions, right? Because this one is only representation in decimal and binary. Am I right?
Yeah.
Okay. So, but this representation does not help us to capture the size of the numbers, okay, in the range of 0 and until 9, and also their ordering, okay? And while it is possible to automate your arithmetic operations such as addition, okay, therefore you need to have a lookup table, okay? Far better to use a representation that is based upon your unsigned binary number. So what is unsigned binary number? So remember, you just learned just now what is unsigned binary number? Do we need to have a positive and negative value unsigned? Or we
No.
only have positive value that starts from 0 until infinity, positive infinity? Which one?
Both also
Ah.
got, I think.
What will be the unsigned binary number? Positive. Start from positive, Sanat.
Uh,
Okay, so bit number binary number representation is this representation is much more better because because of what? Why does this representation scheme is much better? Why?
be, because it doesn't show negative or positive.
Oh, okay. It's okay. Later you'll see the reasons. Okay. So when you use the bit string for numbers, okay, we need to use numeric representation. Okay, can be easily implemented. It is cheap in your computing machinery. Okay, they also need to make it easy to share the data between the different machines. In practice, this means using bit string of fixed length to represent your numbers and agreed how does it be interpreted. Instead of you creating a representation scheme for a particular purpose, we choose a predefined representation scheme. Okay, but it means that we can use a standard algorithm and share the data easily. Okay, but you have to make sure that make sure lah. You have to understand that this when you create a representation scheme for particular purpose, okay, it means that you need to have more possibilities that we will ever do. Okay, just now lah, like just now you have the redundant bit sequence. Okay, maybe we have more than that. Okay, so unsigned for bit binary representation, okay, so which means that you're going to have 16 possible bit string with the meaning that none of them are redundant. We just not to use 6 of them in our application. Okay, guys, are you surviving? But why does we
Yeah.
need to use this scheme? Because the same principle as we employed in the standard decimal number representation scheme. So decimal scheme, we have chose from 0 to 9, where each of the positions that each digit carries mean the decimal place value. Same goes with your binary scheme. Okay? So, unsigned binary numbers, how does it work? We have the rightmost significant, rightmost digit, which known as the less significant in your unsigned binary as the whole number, which is reused as a 2 to the power of 0. Okay, so if you remember the table of conversion that I teach you, I start with 2 to the power of 0 from the here. Am I right? And then we have 2 to the power of 1, 2 to the power of 2, and 2 to the power of n. Okay, so this one would be the first one, which is your less significant bit, which is your rightmost. Okay, and this one, 2 to the power of n, would be your least left hand side, okay, leftmost digit. Okay, and then it will become your most significant bit. Okay. So far, do you have any question? It will be the same thing that I teach you. It's just that I did not use 2 to the power of 0 times with your value. I just directly 1 times 1. Okay, that's why I teach you use the table. Okay, 1, 2, 4, 8, 16, 32, 64. So all of this actually the represent is already converted from 2 to the power of 0, 2 to the power of 1, and so on. Okay? So now do you understand why I teach you using these tables? Instead of I'm giving you this kind of formula for you to do one by one. Guys,
Yes, miss.
okay? So unsigned binary number, each of the following bit string may be read as unsigned binary number. Okay, but then I doesn't prefer you to use this one because sometimes when you use this kind of method, you will tend to have some missing information. So that's why I teach you using tables. Because if you do this one, sometimes the value that's supposed to be times with 2 to the power of 1, you times it with 2 to the power of 0. I doesn't want this to happen, okay? So please do use the tables that will make your life easier and would not deduct your marks. Okay? So now I have questions. How come this value become 19? Can Aisha show me using the table? How was the 10011 become 19 in decimals? Aisha,
Yes, ma'am.
I'm asking you, how does this 10011 become 19 in decimal?
Mm, yeah, I will assist.
Why you use that method? I doesn't want you to use that method. I asked you to use the table method. Aisha, did you hear what I'm saying to you?
Yes, ma'am.
Why didn't you use the table method? Why you use this method? It's okay. Later, I will give you a lots of tutorials to use the tables instead of you use the power to do the calculation. Okay? So, what number range do we get when we have n bit string that give 2 to the power of n possible sequence of 0 and 1? So usually each of them represent a different natural number. So what is natural number? Because okay, later this one you will find out by yourself. Okay, the smallest natural number can be represented by n bit string is 0, okay, and represented by all zeros bit string. The largest natural number quantity can be represented by the n bit string, which is 2 to the power of n minus 1. Okay, where this will be represented by all 1 bit string. Okay, so now let's have a 30 minutes break, okay, before we proceed to the next part.
Okay.
Okay.
Okay,
Thank
Miss,
you, Miss.
I go make breakfast, can I?
Can 30 minutes enough?
Uh,
Enough, right?
okay.
10:30
Yes.
come back here.
Okay. Okay.
Okay? Okay, class, let's start. Let's resume our class. So, finding a binary representation, each time that we want to represent an unsigned numbers, okay, we must find the appropriate bit string. Human being cannot be expected to work with binary because we human does not understand the binary values because we only know that it is on and off, but we doesn't know the on and off is for what, right? So they will use the decimal digit string to represent the unsigned number. But then we still need an algorithm to convert the decimal to a binary, binary to decimal, and hexa, and so on, the conversions. So there are several algorithms for converting the unsigned decimals, okay, into unsigned binary numbers. Okay, this one I already covered in yesterday classes, okay? So I did not want to do it again today. So we directly go to the binary arithmetics. Okay, so binary arithmetic is very similar with our normal arithmetic in decimal. Okay, so we need to do the line up, we need to do the carry in, carry outs, we need to do the borrowings, and we have our rightmost column, leftmost columns, we have LSD, we have MSD. What is LSD? LSD is the less significant digit. Okay? And this is the examples when you do the addition of two one-digit decimal with a one-digit result. Okay. So as you can see that 0, the blue one is the first digit. Okay. The B will be used B will be used white as the representation. For example, we have A plus B, which we put 1 plus 2. So 1 plus 2, we're going to get 3. So 3, there will be no issues. This is a black one. So what if our A is 1, our B is 9? It would be 10. Okay, but you see here, the 10 cannot be represented. It put only 0 because we does not have the second digit. We only have one digit. That's why this one all become red in colors because we have our overflow results that are not being listed out. Therefore, they are having the two-digit results by using two-digit decimal numbers. Okay, so we do not have our overflow because we allow an extra digit of your result. So it means that when we say A plus B, it means that 0, 0 plus 0, 9. So you will get 0, 9. If I said A plus B, 0, 1 plus 0, 9. So we will get 1, 0. So there would be no overflow. But previous one, when we have only one digit decimal and having one digit results, we have an overflow, which is our 1 cannot be written out. Okay, so that's why it become an error. So here they decide to provide a two-digit result. So we have two one-digit decimal numbers. Okay, so there will be no overflow because we allow the extra digit. Okay, so this one I already showed you just now, right? So 0 plus 0, it will be written as 0. 0 plus 1, it will be written as 1. Okay, but 1 plus 0 is equivalent 1, but 1 plus 1 is equivalent to 2. But when we convert into binary, it will be 1 and 0. So 1 and 0, we cannot put our 1 in front of the 0. Okay, this one will be our overflow. Okay, so since we have overflow, it would become our incorrect representation. Okay, so that's why they ask us to have a two-digit output. Okay, so when we have two-digit output, it means that we have extra spaces and it would not having any overflow issues to be occurs. Okay, so far do you have any question for this one?
No.
No,
No.
miss.
Okay, What if we have two-digit binary numbers, for example, A plus B? We have 1 plus 1. What will be our value? 1 plus 1 is equal to, 1, 0, right? So we're going to have our carry out and we have our carry in. So we have 1 as our carry out and then we bring in our 1 into the front, correct? So 1 plus 1 plus 0, we will get 1, 0 also. So we have a 0, we have a carry out, we have a carry in. But this one considered as overflow if we put here. But it, as for now, we only have two-digit results. So the overflow issues is occurring here. So it means that if you only requires two-digit results, this overflow would be an issue. So you did not have any extra spaces. That's why you need to have a three-digit result to entertain the overflow value. Okay, so far do you have any questions? No. Okay. So this one I already mentioned just now. Okay. So addition of two-digit binary numbers with a three-digit result. So in general, when we add together the two n-bit numbers, we need an n plus 1 bit string to represent the result. This may be viewed as an n-bit result with a 1-bit carry. So you can see here, this one would be your value, okay, of the third digit result. Okay, so positional system supports the addition. That's why yesterday I got teach you the positional system support, where we have to know where is our carry out, where would be our carry in. So now I have a question here. Is what type of carry? Sanat, what type of carry is this?
I don't know.
Apa pula you don't know? Kalau, okay, if it is below, what is it again, Mariam? It is a carry?
In?
Yes, correct. It is a carry in because it's still under the value here. If we are put in the top like this would be a carry out. Okay, because it is already carried outside. If you are carry it down and inside, so this one is known as carry in. Okay? Understand, Sanat?
What's carrying it out again? Can you explain?
Okay, for example, 1, 1, 0 plus 1, 1, 1. Correct?
Yeah.
So, 0 plus 1, we will get 1.
1.
Correct? 1 plus 1, we should get 1, 0. Am I right?
Yes.
But we can only bring down our 0 here and put a 1 here. So this one here is our carry in. Because we carry the 0 inside
Okay.
the column. Okay, the same column, we call it carry in. So when this one, we move it to the next column here, this would known as a carry out. We carry it out to the next column. Okay, so this one, so 1 plus 1 plus 1. What will we get? 1 plus 1 plus 1, what will we get?
1.
Why 1? It should be 11, right? 1, 1, right?
Oh, okay.
Okay, so we bring down our 1, but another one will be as your carry in. And this one, we bring it to the front as a carry out. So we put it down, it will be our value here. Okay,
Okay. Mm.
so far clear?
Yep.
So this one that has no because we have 3 digit, right? 3 digit to do the addition, right? So this one, the extra 4th digit known as the overflow. So this would be the extra digit. If we have 3 digit to do the addition, we're supposed to be having 4 digit for the results. Only then this one would not be our overflow. It will be considered as the same value. Okay? If not, they will have an issue which is overflow. Understand?
Yep.
Okay. So this one is the same thing. I doesn't want to explain again. Okay. So digit string of a fixed size. In hardware, we are only interested in a fixed size data item. For example, we have 4 digit binary addition range 000 to 1111. What happens if we try to add 10 and 7? 10 and 7. How come it become 1? How come it become 1? So you need to do the conversion from this value 10 into a binary value. What would be the binary value for the 10 and 7? In binary value. 1010. 7?
111.
Yes. So now 00001. Sorry, this one is a bit 1. So that's why they said 1. Is this correct? Because we only have 4 digit 1, 2, 3, 4, right? So this, when we do the calculation, it shall be 0001 because we does not count this overflow. Right? That's why they said it is wrong when we said it, the answer is 1. Correct or not? Guys?
Yes.
So that's why we need to have a extra spaces which is cannot be used as a 4-bit result because we does not have a sufficient range to adjust our value that is more than the required data size here. Okay? Understand? So when we have
Yes.
10001, only then we get the real answer which is 17. Correct? Am I right? Instead of you only use 0001 where your value is only 1 for this calculation. Which one is correct? The 17 or the 1? It's supposed to be when we do the conversion.
17.
Yes. So far, do you have any question for this one? No? So, when we use a fixed length representation, it makes your machine simpler and cheaper to build. Okay? So, the exchange of your data between your machines also will be simpler. If we decide in advance that all unsigned whole numbers will be presented using a bit string of the same length, we only need one size of your machine. But then, in practice, what engineers would do is they will standardize all of the small set of unsigned whole number representation of a different length, where each of them will follow the unsigned binary representation principles that will be presented in the previous slide. But when we have a fixed length, it will introduce 1 or 2 issues that we need to contend with. Okay? So, this is the pro and cons when we use the fixed length representation. Okay? So when we say it is good because each numeric value it takes up the same amount storage space. So we can know how many memory space that we are required for this kind of things. Okay? And when we do the fetching and storing the numbers, okay, would be much more simpler. Okay? arithmetic for hardware and software is easier for them to implement. But when we go for the consequences, okay, usually the numbers that can be represented would be very short, okay, to be stored. Okay, and they also will have a upper limit of the numbers bit sequence that will be available. Okay, and also your result of arithmetic would not be correct. Okay, because somehow it would not represent the value that we want. Okay, so why do we need to use the 4-bit strings in example? Because the real world data item are represented using much longer bit strings. This will be done purely to reduce the complexity. Okay, so this is when we have 4-bit hardware, but we want to do the addition of two 8-bit numbers. So that's why we split them into 4-bit, 4-bit. You can see. We do the bit slice addition. For example, we have 11011101, right? And we want to add 11110000. So is it is possible for us to add directly? No, because our hardware only allow us to do the 4-bit. Okay, that's why they provide the solution, which is we slice the bit into two parts, which is 4-bit and 4-bit. Okay, and so when we employ the techniques as a bit slicing, okay, we apply the 4-bit right to the left one chunk at one time. We can identify the carry out of the current chunk with and carry into the next one. Okay, so you can see that there would be carry in to the lower chunk and carry out from the lower order chunk. Okay, can you see what would be the differences here? Do you understand the calculation here, guys? So,
No.
no, 1 plus 0, you shall get 1. This is the final answer. Okay, this would be your carry. Okay, carry. 1 plus 0, do you have to have any carry in?
No.
No, so that's why they put a 0. So, 0 plus 1, do we have any carry in?
No.
No, so we put our 1 directly here, correct? 1 plus 1, we put, what will be the value? It will be 10, right? So 10, we bring our 0 here, and the 1, we will put it where? Here. Can you see? This would be our carry, right? Carry in.
Sorry.
Okay? So, 1 plus 0 plus 1. So you will get 1, 0 also. Am I right? So you bring down your 0 here, and this one you bring to here. Can you see? So 0 plus 1 plus 1 plus 1. So you're going to get what? 1, 1 as the value. Am I right?
Yes.
So 1, this is your bringing down value. So your another one you will be bringing to the next one. Okay? And then this one, 1 plus 1 plus 1. You will get what? What do you get? What do you get? Okay? So this is the same thing. It's just that you're going to have a lower or a low order chunk carry out. Okay, and then from lower chunk, you will put it in the high order chunk. And then you have the whole carry out from the whole calculation. Okay, so that is the meaning lah for this drawings, for this techniques. So far, do you have any question for this one?
No.
No. So what is byte? Still remember I said 1 byte equal to how many bit? 1 byte how many bit? 1 byte how many bit?
8.
8.
Yes, 1 byte is 8 bit. So it means that if 1 byte I have 1, okay, when we convert into binary, we have 0, 0, 0, 0, 0, 0, 0, 1. This is the example. Okay, so 8 bit like this. Okay, so this technically the smallest chunk of your machine memory that can read or write in one go. Okay, so each manufacturer made all the hardware and wrote all the software on their machine. Therefore, there would be no communication link between the machine of different types. But once this changed, the standardization grew and grew. Okay, so standardized bytes. The engineer used the standardized length of bit string. Okay. So the machine will be easier for you to build. The specification and construction of your machine will be simpler. Everyone use the standardized part they can produce in large numbers, so everything will be cheaper. Exchanging will be much more straightforward. Okay, so a standard byte is a bit string of 8. Okay, so this one will be the industry standards for several decades until now. Because when we work with whole bytes, will much be easier. Okay. So byte string, 1 byte string is equivalent to 8-bit string where we can accommodate 2 to the power of 8, which is equivalent to 256 sequence. Okay, so when they said an n byte string, which means that you need to put 2 to the power of 8 n, because this n we doesn't know, because we said byte. If bit 2 to the power of n only, right? So when we said 2 to the power of n byte, you need to put an 8 in front. Why? Because 1 byte is equivalent to 8 bit. Understand? Do you have any questions? No? Okay. So what about the numbers inside your machine? So your computer is not a computer if it cannot represent a numbers. Okay, so we take the unsigned binary representation of the numbers and map it onto the collection of electronic signals. Okay, so as we all know, high voltage is 1, low voltage is 0. The 4-bit strings requires 4 signals, like this. 4-bit, it means that 4 signals, 0, 1, 1, 0, 4-bit signals. Okay, so inside the machines, usually the signals are arranged in parallel. So this is known as parallel. 4 wires are required to carry your signal to represent 4-bit numbers. Okay? Can you see this one? So for example, if we have 0, 1, 1, 1, so it means that your wire need to draw as 0, 1, 1, 1, so that it would be parallel like this. Understand? Guys, do you understand this one?
Yes. Yes.
Yes. And why does this is 6 here? What does this 6 means? Because we have 8, 4, 2, 1. If they say 6, it means that we only on for this one and this one. Right? If we said 7, so we're going to have 0, 1, 1, 1. So here would be 7. Understand? What if I say 8? So the value would be 1, 0, 0, 0. So here when we change it, it will become 1 that is in the lighter green. Others would be in the dark green. because it is not activated as a 0. Understand? So when we add the numbers together, okay, so an n-bit adder circuit is used to perform the job to combine two n-bit string in a manner that implement unsigned addition. So we have input A and input B. Okay, so these two things would have different values. Okay, and this would be the decimal representation. This is your carry in and this would be your carry out. That's why when you do this one, you have to make sure that these two things exist here to ensure that there would be no issues. Okay, so when you add up, you're going to get your decimal values and it will become your binary values here. See? Do you understand for this one? Do you want me to
Yep.
explain further? No need. So this one is the operation symbol, where in your logisim you can find this out. Okay. So, so we built an n bit adder from n 1 bit adders, where 1 bit handle out of the n, 3 bit for input A, B, and carry in, and we have 2 1 bit output, which is stand for your sum and carry out. Okay. So input, we have 2 because we want to perform an operation. So this one will be the operation signal symbols. Okay, so we need to have the carry in and carry out, and what would be the output or the sum values. Okay, so far do you have any questions? So far do you have any questions?
No? No.
No? This one easy to understand, right? Okay. So this one, this is what we do when we have a bit slicing technique where we divide them into different slices. Okay, so when we use the bit slicing, we can use build an 1 bit adder. We construct a 2 bit adder, 3 bit adder, and so on by using 1 bit. So each one of the bit you will slice them into 1 bit, 1 bit. But at the end of the story, you will compile them together like this. Okay, so for example, we have 0, 0, 0, 0 input. We have a 0, 0, 0, 0. This one is input A, this one is input B. So we will do the bit slicing. We separate them into single bit. That's why we have bit 0, bit 1, bit 2, and bit 3. Okay? So each of them will have their own carry in and will have their own carry out. Okay, so as you can see that this is the carry in for your bit 0, but the carry out would be bring to the bit 1. Can you see the linkage? And the last bit 3 would have their own independent carry out because there is no longer any additional single bit need to be added for the next row. Okay, do you understand this part? Do you have any questions,
No?
guys? No? This one is easy for you to understand?
Yep.
Okay, so next, adding a longer numbers. We can do it as many as we can. Okay, for example, we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we want to add them up together. We can either use a single bit slicing, or we can do the 4-bit slicing. If we do the 4-bit slicing, we only have to have 2-bit process like this. Okay, 2-bit adders. So you separate your things like this. So the first segment would be going for the first bit adder. The second slice would be go for the second adder. at the end of your story, it will be merged together at the end of your process. Okay, so this would be your carry out, the C out for the first adder, first bit adder. And this carry out would be transferred as a carry in into your the second bit. Okay, so can you understand this figure? Do you have any question you want to ask? Clear, eh? So next, what about the signed numbers? Just now we already done with the unsigned numbers. Okay. So when we counting numbers, it starts from 0 and working upwards. We have seen so much numbers that are represented as a bit string, and how your hardware may be used to implement the basic numerical operation. But we couldn't handle the result of some subtraction sum because we have no way to represent the negative sign. But you have to understand, your computer also need to be able to work with the signed number too. Okay? Suppose we want to represent a range of decimal numbers using 2-digit case. Okay? So unsigned numbers have size only this simple. Okay? So unsigned number have the size and direction away from 0. So we introduce a way to specify the direction. That's why we know it as a sign. Okay? So in decimal, we use negative and positive. But in binary representation, we only have 0 and 1. It means that we have to find a way that is very creative to represent them. Okay? So, for example, this would be the unsigned 4-bit binary value. So, only have 16 possible bit string where each of them represent one of the natural numbers from range 0 to 15. Okay, if we are to use the 4-bit string to represent the signed numbers, some of this will need to be repurposed. Okay, so the obvious way to deal with your signed number is, okay, whether it is the number is positive or negative, we introduce the sign bit. Okay, so the sign would be 0 to indicate positive, the sign 1 would be the negative. Okay, so for examples, our value of unsigned 67 is 0100011, but when we have positive 67, automatically the value in front would be positive. If negative, it will be 1. Okay, so our number representation are fixed lengths because your hardware is a fixed size. Okay, we cannot introduce the extra bit to the bit string in order to represent the sign of your numbers. Okay, so positive number is range from 0000 until 01111. This one is the positive values. If we have 0 in front of your binary numbers, is equivalent to negative values. Okay, so 4-bit signs of magnitude numbers. Okay. So, for example, still 16-bit, but those in the range of 100 until 1111 are being used to represent different number this time. So you can see that if we have a bit string for 0 positive, we have a 0 in front. But if negative, it would be a 1 in front. You can see the differences. Positive 7, you're going to have a 0 in front of the value of 7. If negative 7, you have 1 in the front. Okay, so using the sign bit give us a way to represent positive and negative. Okay, so using n bit unsigned binary numbers representation, we can handle any value or inside the range. But if you are using n bit, we can handle this value using like this. So we need to add a sign, a negative or a positive in front. But this one is no sign in your representation. Okay, so positive 0 and negative 0 actually are represented differently, but then they still have the same value or same definition. Okay, so consequences of the sign bit, it's easy for human being to understand, but if for automation it would be the less convenient. Okay, so there are we have the bit coding for two different kind of things. One is the value in the column of the numbers, whether it is a positive or negative. Okay, therefore we need to be careful to build a machine that interpret your bits right away. So we need to know which bit is the sign bit. We need a definition to tell us which bits to interpret it in this way. Therefore, we cannot grab more bit to the left when we want to represent bigger numbers. So we required to have a different algorithm for addition. We also have two different bit string to represent the 0 like this. Okay, so this would be the example for 4-bit and 8-bit. Okay, for the unsigned. Well, for this one would be the 8-bit and 4-bit for the signed value. Okay, so by adding the two signs, okay, we cannot employ the technique we use for unsigned numbers without any changes. Therefore, we need to use different algorithm for different hardware. Okay, so these things will make your hardware very complicated. Okay, so we need to have an encoding scheme. So ideally is to give a length of bit string should be only one bit sequence that represent number 0. Addition or subtraction should work the same way for positive and negative numbers. It should be easy to spot when your result of calculation cannot be represented. Okay, and it shall be easy to tell whether your numbers is negative or not. Okay, so you need to think it differently. Okay, so pull the all 0-bit pattern on the top of the clock face where the 12 normally go. Go up through the bit as we travel clockwise. 4-bit there will be 16 different patterns. 8-bit there will have 256-bit patterns. While 16-bit string will have 65536 different bit pattern and so on. So this would be the 4-bit clock face. Okay, so each of these will have their own representation. Okay. So far, do you have any questions? No? So 4-bit sign and magnitude, map your positive into your bit string 00 and numbers of negatives to the bit string 100. So some of the bit pattern on the clock are used to represent positive numbers, some of them to represent the negative numbers. Okay, so when the positive, we travel clockwise, okay, until we reach the positive 7. Then they go down from negative 0 to negative 7. Adding 1 has a different effects on the positive and negative number. So numbers that flip from the positive 7 to negative 0 and from negative 0 to positive 0. Okay. So alternative encoding is we are using the two complements. Now still remember your two complement. Okay, these two complement actually came from the going around the clock. Okay, 1 bit string represents 0, numbers go out, we travel clockwise. If number goes down, we travel anti-clockwise. Okay. So as you can see here, 0 to positive 7, negative 2, negative 7 to positive 0. So each of them will travel either way. And you're going to have a number flip between positive 7 and negative 8. Okay? So some same bit string, but you have a different meaning. So in two complement representation, the half of the bit string have a 0 as their most significant bit to represent non-negative. And they have the same interpretation as your unsigned numbers, while the other half represent the negative numbers but in a different way that being used in the sign and magnitude case. Conveniently, we still can use the MSB as the sign bit. Okay. So positive, negative, and 0. 0 represented by all 0-bit pattern. Non-negative two complement numbers just looks like your unsigned numbers with the most significant bits is equivalent to 0. But for the negative two complements, you're going to have 1 in the front for your most significant bit. Okay. So about the two complement encoding, I have explained it just now during our previous slide, right? So I hope you have no issue to understand this part. Okay. So negation. Negation is about a not, a negative. This is the negation. Or we put a not A like this. Okay. So this works for both positive and negative X. For example, the first example, 4-bit 2 complement representation, positive 4 is 0, 1, 1, 0, 1, 0, 0. When we flip all the bit, it will give the value of this one. When it plus 1, okay, it will provide you 1, 1, 0, 0 for the two complements. This is why just now I asked you to do and understand. Okay, so because this one is helping you to do the complement for both positive and negative values. Okay, so far, do you have any question for this part?
No?
Okay, so two numbers are not packed, which is 0 and negative 8. These two things are not being packed, okay, because they are not a complement of, they are not the two complement for each others, okay? So arithmetic addition and subtraction. To calculate A plus B, just do straight. But what if we have one positive value or one negative value? How do we do it? So this is how does it looks like. Okay? So if we in the normal decimal value, it will be easy lah. When we say 5 plus 1, we already know it will be positive 6. If we say negative 3 plus negative 2, we already know it will be negative 5. How about the binary value? Okay, it still be the same thing. How did you do the calculations? That's why just now I want you to really understand about the carry in and carry out, because you will need to implement it here also. Okay, do you understand? So if we say positive 5, you have to put the 0 in front, 1, 0, 1. Okay, and if we say negative 2, negative 2, why does it become 1, 1, 1, 1, 1, 0? So this one, you have to refer back to your clock. Okay, so your clock just now. This one, negative 2. This is the value. Am I right? If you can't remember the clock, so you need to do it manual way. How do we do the manual way? We convert our value into a binary value, which is
0,
0,
0.
1,
Uh,
0, 0, right?
yes.
Am I right? Okay. And then what do? We reverse everything. 1, 0. Okay. And then we do we put the addition 1, correct? So that's why we get 1, 1, 0. So this is the manual way. This would be the fastest way, where you memorize the clock. Okay? So understand now how come it become 1, 1, 1, 0?
Just once.
Okay?
Yes.
Okay. So same goes with this one. Okay? Okay? Do you have any question for this one? No?
No.
Okay. So now I have questions. How come your value is negative 1, but your result is 1, 1, 1, 1? Huh? Can you explain how? Can you tell me how? How it becomes like that? How it becomes your decimal value is negative 1, but your result in binary is only 1, 1, 1, 1. Why?
Because the clock told me.
The clock told you. What if you didn't have the clock? What if you didn't have the clock? Huh. What if you don't have the clock? Huh. What if you don't remember the clock at all? Huh.
No idea, miss.
We use
No idea.
the method you just said.
We use the method that I just said. Okay. So, the result of this one is actually a negative number into complement. So, to find out how does it, what does the number 8 become, it represent, we have to reuse the formula that I teach to convert it back to the normal value, which is from 1111. We need to do the reverse way. Convert it to the first complement. So this one will be the original value, right? And then we convert it to the first complement. We add 1, and then we're going to have 0, 0, 0, 1. Am I right? But 0, 0, 0, 1 is our positive 1. But what if the negative? What if the negative value? If it is a negative value, we shall put it as
Positive.
right. Okay.
Yep.
Okay. So this one should not be issues. Overflow of two complement. So overflow rules in two complement addition, if A and B are both one sign and the result is the opposite of sign, there would be an overflow. So if we add together the positive and negative numbers, no overflow would happen. But if we add two positive or two negative numbers, we may have the overflow. So we combine the sign of A and B to detect the overflow. So we like this. Okay? So far, do you have any questions?
Mm, good.
Good, eh? Confirm, eh?
A bit.
Okay. It's okay. I will give you tutorials later and we will see what happens to you. Okay? So reading the two complement numbers, non-negative numbers with a 0 in the most significant bit are exactly the same as unsigned numbers. The negative numbers with a 1 in the most significant are harder to be read. Okay? So this one is the same thing where you use the value of 2 to the power of 0, 2 to the power of 1. But then this one is already converted with the sign like this. Okay? The bit position and place values is the same thing like what you do in previous slides that I have teach you. Okay, so we have position 0 until 7, but the place value is 1, 2, 4, 8, 16, 52, and 128, where you just implement the bit string inside the suitable column, relevant column, and then you convert and you add, and will get the values. Okay? But you have to think, if the first bit or your most significant bit is 0, it means that you have to times it, you have to make it become a negative values. Okay, what if it is the 1? So this one would be the positive value. Do you understand? Like this. If this one is 0, that's why it becomes negative. But if this one is 1, you're going to have 1 through 8. Only the positive value. Okay? Do you have any question for this one? So this is what I meant just now. Okay? So boundaries, any two complement numbers represent has a largest positive numbers and a largest negative numbers that can accommodate. Okay, in a 4-bit representation of the largest positive, it can be available for 0, 1, 1, 1 to represent positive 7. The largest negative numbers available is 1, 0, 0, 0, which represent negative 8. Okay, so the 8-bit for the largest positive number is would be 0, 1, 1, 1, 1, 1, 1, 1, 1, which is positive 1 to 7. While for negative, it will be the reverse value of your positive 1 to 7, which equivalent to negative 1 to 8. Okay, do you understand? Negative boundary numbers, you negate the largest positive numbers will always work fine. Okay, you need to flip. For example, positive 7. When you convert to binary, it's 0, 1, 1, 1, 1. So you flip, you reverse them. You will get 1000. Okay, then we add 1, we get 1, 0, 0, 1. So this would be the complement of representation of negative 1. Okay, but negating the largest negative numbers results in overflow. Okay, which the 4-bit 2 complement represent of negative 8, where we're supposed to get positive 8. But since it is outside of the range of the representation, it will become an overflow. Okay, so 2 complement in hardware, no 2 complement works in theory all as well and good, but we need a circuit or device to perform the operation that can tell us the result, what are they are good, whether it is reliable or not. Okay, here we look at some such devices. Okay, negation doesn't mean it makes it the value negative. Okay, but then it means that we have to multiply with negative 1. Negating a positive numbers give a negative twin. But when you're negating a negative numbers, you will get a positive values. Okay, so we need a circuit that flips all the bit in numbers and add 1 into the result. So we use an array of NOT gate to flip all of this bit. Okay, we can then add 1 by passing the result through the incremental. So this will be the example of 2 complement negation circuits. Okay, but you have to understand that if you only have this one, it means that we does not have it complete yet, because it does not entertain the overflow. Okay, it provides us no means to detect the overflow, because when we add the values that would have possibility having the extra bits, the overflow would not be detected and you will end up getting the wrong interpretation. Okay, so suppose we have 4 bits complement numbers that we want to represent as an 8-bit 2 complement number instead of below. Okay, so this one will be the easiest way for you to understand. When we have negative numbers, we put 1 as a most significant bit. Okay, so representation would be example like negative 3, positive 3. Okay, so the front bit value would be 0 and 1. You can see this. So this would be the 2 complement value, 8 complement values, and 16 complement values. But still, in front of the representation is 1. It would not change to 0 because our initial representation is negative 3. Okay. So, extending the 4 bits of 2 complement to 8 bit, we want to represent the same value as 8 bit string. We need to pad the left hand and with a copy of sign bit where we know it as a sign extension, like this. Okay, like this. The same principle holds when we want to extend two complement representation to 16ths or longer. Okay, so just now we have a 4-bit, right? For example, our 4-bit is 0001, but this is 4-bit. But what if I want to change it into 8-bit? So it means that if the most significant bit is 0, so we need to add 40 in front, okay, and then it will become the other 4-bit will be maintained. So what will be the first original bit? It will become the extension to the front. You will be repeating it. For example, if you want a 16, so we check the original 4-bit. The most significant bit is 0, right? So you have to add another 14 bit of 0 because it is an extension sign. Okay? So far, do you understand this one?
What if it's 0 is?
Because 0 is the negative values like this.
No, I said, well, what if 1 instead
So
of
if
0?
1 instead of 0, then you just repeat 1 lah for 14 times. Like this. You have to refer if the original value is 1011, right? So it means that this is 1. So you have to repeat it 4 times for 8-bit. If a 16, you have to repeat it for 14 times. Like this. So the 1 here will give you the extension sign. How many times? Based on the requirement. Understand?
Yes.
Okay. So, this is the extension circuits. How was it looks like? Okay? It's just that you extend the value based on the most significant bit for the original value. Okay? So it's just that this is the original value. When you have extension for 8-bit, you just add another 4-bit that is follow the most significant bit here. So that's why you can see 0000. Understand? If your most significant bit is 1, all of the extension sign would be 1. Okay? Understand?
Yes, miss.
Yes, miss.
Don't have question, eh? Currently, we are in the... Uh-oh. We still have more slides to be done. Addition of two complement numbers. Addition can be performed in the same way as the unsigned number except for your carry out is being ignored. Overflow will occur when the result of adding two numbers causes an inappropriate change in the sign bit. Okay, you need to add two positive numbers to give the result with a sign of bit 1. And you add two negative numbers, it will get a result of bit 0. We detect an overflow by comparing the sign bit of two inputs with the sign bit of the sum. Okay, so this is the example when you use a single adder and when you use the bit slice adder for the two complement addition. Okay, can you see the differences? Okay, so this one, the two of them does not covers for the overflow. Okay, so it means that when you do these two things, even though your answer is correct, but then it does not entertain the overflow if the value is having more than this input. Okay, so for us to know the overflow, we need to compare the sign bits of the two input and the sum. Okay, usually the most significant bit in each case, in the 4-bit representation, the bit is 3. Okay, well, the 8-bit representation, the bit is 7. Okay, so that's why I want you to really understand the digit placement. Okay, so how do you find out which bit is you are using the formula if there is 16? Okay, it means that n minus 1, it would be the value, which one that you need to use to compare. Okay. So this is the overflow detection. So for a 4-bit representation, overflow has occurred. Bit 3 of A is the same as the bit 3 of B. Okay. And the bit 3 of the sum is different. Okay, this is an easy circuit where we have A3 XOR B3 and A3 XOR S3. Okay, so we can add the overflow detection to an adder as in the next figure. So this would be your overflow. This is your carry in, carry out. This is your logic gates. This would be your input. This would be your output. And this is your process. You add or what. Okay. So far, do you have any questions? No?
No.
So two complement subtractions. Natural subtraction are much more harder to implement when we are using two complement representation, but the subtraction of A minus B can be performed easily by negating the A and adding it to the negating the B and adding it to the A. So there would be no borrow in or borrow out. It's only have carry in and carry out. But usually your carry in will be set to 0 and your carry out will be directly ignored. So overflow can be detected the same way as your addition, like this. Okay. So two complement subtractions circuits. So this one have your two inputs A and B, but the heart of this circuit is an adder. Okay, you must be thinking that why we are using adder, right, for the subtraction, because we have already have our negate here. Just now they mentioned, right, A minus B. So if we separate them, we have a positive A and minus B. That's why our B, they have a negate, which is a not 8 here. And they do the addition. Okay, so you will get the same values. Okay, do you understand this part? Okay, comparing two complements number. When you're programming, we often compare using the greater than, less than, equivalent, and so on, right? But this one cannot be easily done by using bit by bit comparison. But once again, we doesn't need to rebuild 6 different circuits. It's just that we can do the comparison in different way. First, we can do the subtraction, and then we can examine by looking of the two things. If it is 0, then A is equal to B. If it's not 0, then A is not equal to B. If it is negative, then A is less than B. Okay, so you can see that it will be much more easier when you do the comparing instead of you are doing the comparison operator. Okay, in the circuits. Okay. So comparator circuits, we need a gate and a splitter to do the subtraction. So we need to have a new input. One of that is 1 when A is equal to B. Another one is A is less than B. So the circuit needs to compare a pair of unsigned numbers or a pair of two complement numbers. Okay. So I think I have exceeded our last time. Okay, but then I will finish the recording. So if you want to stay, you can stay. If you want to leave, you can leave, because I only have 1, 2, 3, 4, 5 slides more to finish to do chapter 2B. We have a chapter 2C to be covered. Okay, you have class after this? Guys?
No.
No. Can I finish it for the nice slide?
Yes.
Okay. So sharing devices, if we adopt a two complements representation of signed numbers, okay, so we can employ the same device as we used to perform the arithmetic operation, but the results, how it be interpreted, would be different for two different kinds of number representations. Okay, so a hardware device just deal with the bit string. and it does not even know what exactly the kind of numbers that being manipulating. But you as the user of the devices usually will know what would be the numbers that being used. Okay, so your hardware will provide a tools that can use to interpret the results of your calculations. Okay. So flag signal, this is the tool that takes the form of flag signals, where the flag can be set as raised when it is 1, lowered when it is 0. So user, programmer can tell the great deal about the calculation from which of the following flag signal are 1 and which one is 0. So usually the carry out would be represented as a unsigned. Overflow would be the 2 complement, negative would be 2 complement, and 0 would be unsigned or 2 complement. Okay, so the flag sign, you have 4, C, O, and Z. Okay, so this C, O, and Z, you can see it here. This one, Z flag, negative flag, carry flag, and overflow flag. Okay. So this would be the flag outputs for your addition. We build a multi-adder with the 2 calculation flag, which is C and B, and 2 result of flag, none, negative and 0. Okay. So when we say about carry flag, it's equal to 1 when your unsigned addition goes out of range. Overflow flag will equivalent to 1 when a 2 complement addition goes out of range. Okay. Negative flag will equal to 1 when your result of complement is negative. But 0 flag will become 1 when your result of addition is equivalent to 0. Okay. We built a multi-adder of 2 calculation flag C and V and 2 result flag N and Z. But you have to remember, a circuit cannot tell what kind of number it is manipulating. So all flag signals are produced no matter what. It is you as the programmer to work out which one is relevant. Okay? So the pro and cons. The pro, we can know all the positive numbers that is start from 0 and negative numbers start with negative and with 1. Arithmetic is easy to implement in hardware. Negating the numbers is simple and only one representation for 0. But the consequences, 2 complement representation of negative numbers are difficult for humans beings to read. Multiplication and division are more difficult to implement. Okay, so that's all for 2B. Okay, for 2C, I will continue it in next class. Not tomorrow, but for the next online lecture class. Okay. So for tomorrow class, please be on time because I want to give you tutorial. Okay. So I think that's all for today. Thank you, class. See you when I see you tomorrow.
Thank you,
See you,
Miss.
miss.
Okay. Thank you,
Okay.
miss.
Bye bye.